we'll just take a quick look at our agenda. So um, primarily, this is going to be focused on working with actual models. We'll have a little bit of PowerPoint in between there. But we'll try to keep that to a minimum and just focus on preparing these simulation models. So this session isn't a beginner session for simulation. There should have hopefully already been one of those if you wanted to go through it. This is more geared towards working with larger models, and we run into this question a lot of, well, how big of something can we analyze in SOLIDWORKS simulation? And kind of the approach you might use to do that changes quite a bit. The way I'd set up a single part or a assembly that's just a few pieces compared to the way I'd go about setting up something that customer sent me that's 500 parts or more is going to change pretty drastically. So that's what I wanted to talk about and kind of introduce you to some different workflows you might not use before, and a whole bunch of productivity tips and new features and things along the way. So mention the resource PDF, scroll up in the chat to access that. This first case study, I'm calling it a case study that I want to work through with everyone. Some of the key steps is a mold. And this is, both of these case studies we'll talk about were based on customer applications that they were interested in analyzing. So this one is it could be an injection mold or die cast mold. And this is actually the files we use from our mold design training class. But the idea was to basically apply the pressure that the mold would be seeing internally to the cavity faces that would be exposed to the pressure. And then basically you'd fix the other half of the mold and you'd apply the clamping force that the mold would be seeing there, and basically just take a look at the deflections, primarily the deflections in the mold, but also the stresses around the mold cavity and things like that. So molds just happen to have a whole lot of parts when you get into all the ejector pins and slides and fasteners and things like that. So they tend to be good candidates for simplification, and that's what we'll be looking at. So one more second here before we dive a little further. So if we talk about the things we would need to absolutely incorporate to have this be realistic, and this whole thing is kind of premise. I want the premise to be setting up like a first pass analysis here for both of these case studies. So we're not going to be necessarily using the most realistic boundary conditions, but we want to have the correct physical effects in there to represent and kind of proof of concept, prove that this type of analysis is possible in SOLIDWORKS simulation. So I definitely want to have contact between the two mold halves. In order for this, pressure to work, it's going to be pushing in two different directions on each side. We need to have like a no penetration contact between those two halves. So you might know no penetration contact slows down your study quite a lot. It's a lot more intensive of a calculation. So try to use it as sparingly as we can, but definitely need it there. And then the other components that make up the stack of the one side of the mold or the other, I'll just apply bonding to those. So that's a pretty big assumption, but where if you look at them, they might be all bolted together and things. I'm doing that for this first pass just to speed up the solution. I mean, if I could put in a whole bunch of bolt connectors into there and use no penetration contact between them, but I'd be looking at really extending the runtime, and it would be something to investigate if that's necessary or not. So I want to get rid of as many individual components as I can. In this case, you may not always want to do that. You might want to leave, things like fasteners, like pins, explicitly modeled in there if you need really accurate local contact stresses around them. But in my case, we're just focusing on the overall picture, overall deflections and things. So it's a great candidate to suppress out all those fasteners and replace them with virtual connectors inside the simulation. So I highlighted there those virtual pin connectors that I'll be using. We have virtual pins, virtual bolts, virtual springs that can be defined to replace physically modeled fasteners. And then finally, where we're talking about individual parts and things like that, we want to potentially simplify the geometry a little bit. And also, we want to put the mesh refinement very carefully where we need it inside the assembly. So things like those detailed surfaces on the cavity, I'd need a lot more mesh control than I would need on some of the big plates there. So the general things we'll be doing, looking at suppressing components. One big consideration there, if you're working on an assembly, if it's your production model, your production model that everyone has released, you need to decide if you want to preserve that and use a whole bunch of configurations to basically stay completely associated to that model. Or if it's a pack and go copy of the files, then you can be a little more quick and dirty in terms of how you simplify things. If you're getting a step file or any kind of neutral file, then you completely don't have to worry about the way that you simplify it. So when I get in there, I'll be assuming I don't need to really preserve all the subassemblies and everything exactly. So that's going to speed it up quite a bit for me. But we'll be using tools like assembly visualization, select by size. We'll look at that. And then on the part level, a variety of methods that we'll get into. So this is, again, just really like a crash course to hopefully expose you to some of these larger scale analyses. Because a lot of times I get an assembly and it might be 500 parts, a couple hundred parts, but by the time it's down to the core pieces that are actually relevant to the simulation, it might only be a couple dozen parts that are left over. So let me shut my webcam here just so we can focus on the SOLIDWORKS, because I know that kind of blocks off the corner of the screen there. So I have this first part is going to be just CAD preparation, essentially. So we have the mold and a certain number of components in it. We can check how many parts we're dealing with by just evaluate and performance evaluation. And maybe some of these tips were gone over in some of the other good sessions before. But so total components 126 is what we're starting with. Um, and what I want is like a quick way to identify the fasteners that I can exclude. I don't want to be selecting all these one by one. So there are some selection shortcuts. If I right click into space and I use the select pull down, there's things like select toolbox. So if these happen to be toolbox fasteners, then I could select them all. These aren't toolbox, so maybe they're from McMaster-Carr or another website, so I can't rely on that tool. So all I've done on this model is just change the exterior pieces transparent so we can kind of see inside a little bit. And I'll introduce you to my favorite tool for this type of thing, which is the assembly visualization. Um, if you don't want to use that, there's like a right click other trick we can do called select by size. If you right click and select a little pull down arrow under here, there are other tools inside SOLIDWORKS like power select or select by size. So select by size will do like a really simple version. Lets you just choose kind of a characteristic size like the 15%. And when I click OK, it selects everything that happens to fall under that threshold. So that's useful. I could suppress those components if I want to. But the assembly visualization just gives quite a bit more control here. So this will color code your assembly, and by default it's in terms of mass. If you click that little arrow on the right, I can switch that in terms of volume, and then I can sort. So now I can sort where um, everything on the top is the smallest volume components, and I can basically just shift select these. Sometimes it can actually be faster to just choose the components you want to keep. So I could choose the components I want to keep and then right click and invert the selection. And when I invert the selection, it would select everything that's not those things I just had. So that's really handy also. But in this case, I would just kind of shift select the components I want to be removing. I can control select any that I don't want to remove. And then in this case, I'm just going to right click and suppress to get those off the screen. Again, if we wanted to be preserving configurations, I'd actually need to open each subassembly and create new configurations on each subassembly for the components I'm suppressing. In this case, I'm, again, not worrying about that. We'll assume it's a kind of broken off copy of the model. You may see mates and things break, and that's just a consequence of doing all that suppression, because suppression does affect all your mates and in context things in the assembly. That's the real basics of it, kind of extreme simplification, fast, using assembly visualization. That's my really recommended tool. When we look at on a part level, if I go to pop one of these cavities open, there may be details in the part, and commonly it's things like text that's cut in that you just shouldn't need in the analysis. I mean, um, text that's cut into the model, I think most of us probably know, is one of the big things that can increase the file size, increase image quality, and all these other concerns inside SolidWorks. So when you're all the way zoomed out and you're looking at something, you might not realize where the problem areas are, whether it's on an assembly or a part. So one of the tools I like under the Evaluate tab again, there's Check and Geometry Analysis. And I will be using like the last 10 minutes of this session. We'll try to save for Q&A to go back through those if there's questions that come in. Um, just wanted to throw that out. But check is probably one of my more favorite ones. If I check the model, that'll identify things like faulty faces, if there were any from maybe a bad import, let's say. But it's also got a little short edge check I can do. So if I type in a value that I want to say is what qualifies as a short edge here, and then click check, it'll put these big arrows to where those areas are, so I can see like it's identifying essentially this text region for me that has much shorter edges than everything else in the model. So short edges naturally become a problem in simulation because we'll need to generate a mesh, and the mesh elements need to resolve those edges to get the mesh to generate. So that can help you identify potential areas for simplification if you need it. And all the simplification I usually try to say is just only if you need it. Usually I do all this in response to trying to get the model to mesh and then seeing that there's some kind of problem. Then I go and do simplification. So we may want to remove this text. And I happen to have a SOLIDWORKS feature here, but there may be other cases where like it's a mirrored part or imported part where you don't have access to the feature history. So there's a number of tools you can use to kind of what we call direct edit or simplify the model when you don't have feature history. There's a direct editing tab you can turn on by right-clicking on your SOLIDWORKS Command Manager tabs and going down to direct editing. And there's a command called delete face. So this one's pretty handy. Delete face allows you to kind of directly remove faces. So if I zoom in far enough to see one of these letters, I can click on it, and then I can use these little selection toolbars. I need to actually select the one that says all surrounding faces. So this is the finicky thing about delete face. You need to select like all the side walls and everything that you want to remove there, not just the bottom face. Otherwise it won't go. And then when I click the check mark, it'll directly remove that. So again, just suspend your disbelief that we can't just suppress this cut extrude feature here for this example. Delete face is one tool. Obviously that would be kind of repetitive to delete all these letters. We could do it all in one feature, but it would be a lot of selections. So I just find that a lot of times people forget that if it was an imported file, you can also just extrude or extrude cut over things too. So, there's nothing to stop me from creating a sketch, just drawing a rectangle over that whole thing I want to simplify, and then extruding it a certain distance. And you can just go blind. You have to be careful though. If I go blind and I just set it a certain distance on a part like this, a cavity, it might have internal features. So that would create some weird things going on in there that we might not necessarily want to do. So just bear that in mind if you're doing this form of simplification. I'm going to do an up to vertex condition and just set it to the bottom of some of this text here to get rid of that. So that's some of the simplification you can do if you don't have access to the feature history. Then some other nice tools to use on the part level if you want to think ahead to the simulation. We can set up selection sets. So when you're in a simulation setting things up, frequently you'll be selecting a whole bunch of faces. So I can use shortcuts like select tangency there to select those faces. But I can also go in and continue adding more faces to that selection if I want to. And if this is something I'm going to reuse, like this could be for a force, and then I might also, so this would be where the pressure is applied, could also be where I want to apply a mesh control. If I just keep holding shift or control and then right click and space, I can go to Selection Tools and then Save Selection and create a new selection set. I think I already had one there, but selection set will be like a quick reference you can come back to, and it lives in your feature tree right here. So you'll see selection set. That's 90 faces that I can just basically reselect by just clicking on them from here. You could rename that if you want to. Um, then kind of thinking ahead to the assembly level, uh, I might want to measure some of the tiny little features on the model. I mentioned I'll want to use mesh controls. So if I just measure things like maybe the tiniest feature I can see on here, that fillet is about 3 millimeters, it looks like. Just kind of pick some of the smallest features you might see. I really like to do that just to get a ballpark idea of what size elements I'll need to be using. So I know if one of those fillets is around 3 millimeters, then that's probably the bare minimum element size I'll need to be using. And I may even create a simulation study just on this part if this is like one of the more detailed parts in the model. This particular one's not that crazy, but create a simulation on here and try to create a mesh. So I could apply a mesh control, which is our local refinement to just refine the areas we need. And I could reference one of those selection sets if I want. You'll see this kind of crawl in here. This is going to tie in with one of my other tips you'll see, which is if you shut off the preview behavior, you can speed up these types of creation of loads and fixtures and things like that. But it's kind of crawling around, loading in all those faces from the selection set. Still better than me clicking them myself, certainly. And then I could key in the mesh size that I want. So kind of based on those measurements that I took, if I said it was 3, maybe we go a little bit smaller than that on the mesh control. And then generate the mesh here. And we'll look at a technique later that allows actually importing the mesh controls from a child study onto higher level studies. So yeah, and the reason we do this, the reason we use these mesh controls is to basically put the resolution where we need it. You know, you think about this number of elements or number of nodes in the simulation is going to ultimately determine how long it takes to run. This is one of our high areas of interest, so we'll want to put more refinement in these areas than some of the big backer plates and things that might be in the mold. They allow us to pick and choose where we want to focus, and overall that's going to help our performance and still help our accuracy. One last thing, if you're working on a multi-body part, sometimes you import a file, it might look like an assembly, but it's a multi-body part, it's got a whole bunch of bodies in the tree. Then kind of like the delete face command, there's a delete body command you can also use. So sometimes that's a problem, or if there's like wires and routes and things like that in there, you may need to delete those out if they're just not necessary to the simulation. But if they happen to be a body, use this delete body command. Okay, so that's basically all I wanted to show on the geometry simplification side. Now we can start to talk about a little bit of an aside before we go into the simulation setup. I wanted to mention some of the new features in 2021 because there happens to be a whole lot of them that are relevant for large assembly analysis. So I also attached in the chat at the very top in the chat, if you scroll up, there's the What's New document from SOLIDWORKS that's got all the features listed. There's about 20 pages just on simulation. So they did some pretty major stuff here. They have the blended curvature based mesher, which was already an option before, but this year it's got a completely new algorithm pulled down from Simulia, as I understand it. And it takes really good advantage of multi-threading. On my system, on the second case study I'll show, it pegged my CPU at 100% for a long time while I was meshing, and it got it done in like a minute. So um, very impressive multi-threading, and they aim to get some of the benefits of both the standard and curvature-based mesher that we had before. It does require incompatible bonded contact, if you're familiar with that, but they also improved that a lot too. So I'm really happy with this. I've been testing it quite a bit and have been impressed. And then again, large problem solving. They enhanced most of the solvers also for 2021. So The Intel Direct Sparse was a really fast solver we had, but it was kind of limited by problem size. Now that's enlarged. Supposedly there's no cap anymore on the problem size that it can analyze, just a matter of how much RAM you have. And then the other solvers, like the iterative solver, also improved to be more multi-threaded. So they have a graphic there showing 2020 versus 2021 runtime for a really big problem. So kind of all across the board, from what they've announced and from everything I've tested, we've seen some great things in 2021. One thing to be aware of going into it is a lot of terminology got renamed for 2021, which I think long term is a good thing, but it can be confusing for right now for people upgrading or down the line as you upgrade. Um, the contacts specifically, now they've called the contacts interactions. And what we used to call no penetration or the sliding contact between two components, now we just call that contact. And that's pretty consistent with other software packages. Like if you look at the Simulia, Abacus packages, the higher end simulation softwares, they all use that naming scheme. Usually we only say contact in FEA terminology if we mean that sliding type of no penetration contact. So in 2021, we just had bonded, contact, and then the free condition. So a little bit of terminology changes there and enhancements to the contact also. So I just wanted to point those out, dig into the what's new PDF, at least the simulation section if you're interested. You'll learn a lot more about that. Um, one of the things I will do is I'm going to mix draft and high quality mesh. So you can look here at some of the mesh elements we have available in SOLIDWORKS Simulation. This isn't new. This is just what we've had to choose from. Solid and high quality, draft and high quality elements. High quality is always the default. You can see it has, looks like double the node, a little 2.25 times the nodes there. And then we have the shell mesh, which we'll talk about later, double the nodes for the high quality. So the high quality, the thing to know about it, it gives you better results in almost all circumstances. If you were to use the same refinement of just the draft quality mesh, you'd see that it would underpredict stresses and displacements. And there's a blog article about that. I included it in the resource PDF so you can learn a lot more. Why might you want to use draft quality though? Well, if you're just setting up your study, it's going to just speed things up while you're trying to dial it in. And then it actually ends up in practice using quite a lot less calculation time, quite a lot less degrees of freedom. It's more than just that 2x that you might think looking at it on an element basis. In my testing for solids, it actually goes up to 8 times less degrees of freedom, which is what's most closely related to how long it takes to solve. So in the appendix of that resource PDF, there's a whole bunch of explanation on that if you're interested. So uh, as of 2020 version, we're able to mix the two. It used to be all or nothing. You had to choose all draft or just high quality. So we used to say, well, just don't use draft quality if you're after, decent results. But now that we have the ability to selectively choose it, we can basically use draft quality in like regions of not very much interest and use high quality mesh in the areas where we need it. So it enables that type of balancing act that we can do. So you'll see that in there. And then I also just disable some options. When problems get to a certain size, there's some simulation options I see, like these two here. I'll show you them in simulation. They actually both have warnings on them that they require more time. And that can start to be a lot more time when you get into a bigger study. So let me go back into SOLIDWORKS and show you these things. And these are identified also in the PDF. But under your simulation pull-down menu, when you have simulation loaded, you can go to the options right there, and you'll see what I'm talking about. It's right on the bottom of the screen. Load all simulation studies when you open the model, and hide excluded bodies and show the material appearances. Both of those can end up adding quite a bit of processing time as you're working with studies. So I'd like to clear those out. And I'm going to jump ahead a little bit to the version of this model that has the setup, but we will look at a lot of the setup steps here ourselves. So I'm going to open up the model that's been simplified. and we'll have the full results there, but for right now, let's look at kind of the work in process. And so one of the big assumptions too is, in an injection mold press, there would be platens that squeeze this on each side. Those I don't have represented here, but that would be a nice thing to add in um, for like a more detailed pass eventually. Um, so in terms of the setup, I have a lot of it here, but I don't have everything defined yet. So we don't have any pin connectors set up. We have the fasteners suppressed, but no pin connectors. And there's also some contacts I need to place. So we just have the global bonded contact. I like to point out that you can put simulation shortcuts right on your shortcut bar, or you can use keyboard shortcuts for simulation. So it's not just SOLIDWORKS. As long as you have the simulation add-in loaded, you can go to the customize options, and then in any of your user interface customization, you'll have categories for simulation right here. So you can drag all these simulation icons. So I have pin and contact on my shortcut bar because those are things I'll be using a lot setting up this particular assembly. So whatever shortcut method you prefer, you can put right on there. So let's try to add the pin. So I'll go to pin connector, and this is also going to sound funny, but I highly recommend that you pin the menu, this little thumbtack right here, when you have multiple things to place, and you have this little pin icon. That's going to keep the prompt open, and it's going to keep the settings also. That's the bigger thing. So if I clear the settings I want to be using, like I'm not going to use this retaining ring option that would prevent translation because I want these to act kind of as slides. Then I can just make my selections. And so for the pin, you want to select a pair of faces there, concentric faces. And then the other thing I can do to speed this up is the right click menu. So I'm not sure if you can see, but on my mouse cursor, if I right click right now, it's going to actually place that pin, and it still kept me in the prompt because I had it pinned, because I had it pinned down there, kept me in the prompt, so then I can just make my next set of selections. And so if you kind of get into a rhythm with this, it can go really, really quickly for any of the simulation types of things that you're placing. And I am also using a 3D mouse. I do really recommend it for um, simulation setup or any like large assembly simplification, just because it makes it a lot more relaxed of a process for me than rotating around like crazily. When you're done placing pins though, with the menu pin down, when you're done placing anything, you'll need to click the little X to get out of it, and then we can see the 4 pins that I just placed there. And then we could basically do a similar thing for the contacts, which are now called interactions, component interactions here. I would go into the local interaction prompt and then choose the type I want. So just regular contact. Again, contact will be no penetration that you're used to. And then I just start selecting sets of faces. Again, I could pin this down and start selecting sets of faces that want to be included in that set. And then I can right click my mouse, and it puts me down into the next prompt, and I can choose the opposing face here. And then if I right click, let's see, this one, yep, it created it. So now I can just, again, go choose the faces I want, right click to go to the next, it's putting me down to the next property pane down here, and then just left click, right click. So very, very quickly I can place these contact sets. And I'm sure you're probably aware there's more automated ways to place contact sets too. There is global contact that we can rely on to generate the contact interactions, but it tends to be that the more manual methods you use, like these local contacts that we define by face pairs, they have the better performance. So it's just a trade-off there between, if I do a global, I could do a global no penetration or something like that, global contact now, but you'd be relying a lot on that global interaction to go through. And we still have one of my favorite tools, the contact visualization plot. Now it's the interaction viewer. So this will highlight for me all the contact interactions that are visible. The model, I've been working on the model in an exploded state, in an exploded view, which SOLIDWORKS Simulation lets you do. So when I go to this screen, it's going to show me a collapsed view. And I can see the areas where I have contact applied currently, the purple faces. So that's the no penetration interactions. And then everything in red is where the bonding is being applied. So that's a useful tool to kind of visualize where you have your contacts acting. Okay, and then in terms of setup, we have a mesh refinement, mesh control placed on those tiny little faces of the cavity. So I think that's about the major steps I wanted to show. So I'm going to actually go to the version that's got some results so we can look at quickly. There's also some components here I might have excluded from within the study. So if you didn't want to suppress them from SOLIDWORKS, you can always right click and exclude from analysis directly from within the simulation study. And that's what will gray them out here. So it looks like the pins, for whatever reason, when I was setting this one up, I actually excluded those from the simulation. That also gets around that issue of what we were talking about causing configuration problems and things. If you exclude from the simulation, then you won't have those concerns about file management. But I just find if I can, that as much as I can simplify before I go into simulation, it's better for me. So that's something you can look at. So I'm going to show you the mesh that was generated here. And what you'll see is that this is probably a little bit of an extreme oversimplification, but every component besides the cavity, I toggled to that draft quality mesh. And the way you can tell that is by the way this little tetrahedral looks here. It's got straight sides. They also call those linear elements. And then there's four components that have the second order high quality mesh, which is the default. So any component you can right click, as long as you have all solid mesh in your study, you can apply high quality or you can apply draft quality selectively. And it's also color coded. So the high quality elements are blue by default and the draft quality are this kind of orange color. So I'm not saying that's the ideal thing to do in this situation. And I think I definitely could have done the whole thing in high quality if I wanted to, but that resulted in a pretty reasonable runtime. This thing took about, I think, 1.5 minutes to mesh. So if I show the details, 1 minute, 20 seconds to mesh, if you can see that little tiny text there. And then the solve time was around 24 minutes. I think it was 24 minutes. That's almost entirely because of the no penetration contact. So if I didn't have that no penetration contact, I think this probably would have solved in a minute or two. But with that in there, it took a little bit longer to solve. That's one of the big contributors to our solve time. So we want to keep that no penetration contact to a minimum when possible. So we can see the localized stresses around the cavity and then overall displacements and things. What we see on the screen is a very exaggerated scale of the displacements. And again, this is where probably if we had the platens of the press pushing on this, then we wouldn't see as much deformation either on those. But basically validated that we can do this type of analysis as like a bare minimum first pass. And then from here, I could copy the study and start adding in more no penetration contact, more mesh refinement, whatever else I want to do to bring the simulation even more realistic. So I highly encourage you to kind of get that baseline going first before you turn on every option under the sun. I think the presenter yesterday in the general session said he even just starts with a single part, right? Just start with the bare minimum detail you can, and then include more as you prove that that base study is running. And that's more satisfying also because you're not getting stuck. So you could even exclude almost all these components and then gradually I can just right click and start including them back into the analysis. But once you have a good sense of experience of what simulation can and can't do, then you can start going a little bigger out of the gate, I think. So some other tips we showed: pinning the menus, using the right mouse button to advance, uh, customizing your shortcuts, and also use the selection sets if you want to. All these tips are in the PDF, the resource PDF. So I want to switch gears a little bit now with you if we can and talk about shells. So that model happened to all be solids. But shells get used a lot. They get used for sheet metal. So if you have sheet metal parts, they automatically convert into shells in SOLIDWORKS Simulation. You can easily convert shells from within SOLIDWORKS Simulation. If you want to, you can convert something that was a solid into a shell. But also anything that happens to be a surface body in SOLIDWORKS will come in as a shell in simulation kind of natively. So I want to expand on that. I did recently do a good YouTube video. I think it's good, at least. I'm biased. 20 minutes long. It's linked in the PDF for like a more intro primer to shells and the various ways you can define them if you want. What I'm going to show next is something I didn't show in that video. And that's a trick I like to use when I have a whole lot of shells to define. So when it's more than just a few shells I need to define, I'll use this trick. And I've already kind of performed it here, so you can see these pieces of this conveyor represented by surfaces. So I'm going to undo those changes I made. I have some suppressed components. So here's another selection shortcut for you. I can right-click my little mouse icon and select suppressed, and that'll select all those suppressed components, and I can bring them back. And I apologize. I'm going to pick up the pace a little bit here just to make sure I can get through the content I wanted to cover. So to convert a lot of shells at once, I'm going to go to the assembly. I'm going to go to Insert Components and click the little arrow underneath it and insert a new part. So this is going to be in context modeling. So you just choose one of your base planes, and then now you're editing a new part that you placed into your assembly. And then we're not going to sketch or anything like that. I'm going to use my Surfaces toolbar, which you can turn on. Again, Tabs, Surfaces. And I'm going to use Offset Surface command, which normally would offset a surface, but if you set it down to 0, you'll see it become the Copy Surface command. And then I can basically just copy whatever faces I want out of the model. So this is again for like extreme simplification. When you have lots of shells you want to create, I will just keep rerunning this offset surface command, and essentially I want to pick also the sides of the surface that would actually touch something. So like the contacting faces of a surface, because then you'll get to pick up the automatic bonding still with this. So basically, if there's components that I wanted to convert to shells in here, I can just keep selecting them, and each one of these is going to become eventually a separate shell inside SOLIDWORKS Simulation. But because of the way I'm doing it, I don't need to create separate configurations as much. I don't need to modify my model very much. What I've done is now I have a part here that's going to represent all the shells. And then I just need to take the components that I converted them from and suppress those. So then now I have surfaces where those solid parts used to be. And that way, if I go into a simulation very quickly, we will see that in the parts list, they actually conveniently kind of get grouped into one little part because it is a multi-body part. And I can edit them, and I could assign their thickness. So you need to have a thickness on there before it will run, or mesh even. I talk about that in that video. So just to prove to you very, very quickly how we can convert a bunch of things. Thought I created the mesh there. Maybe it's thinking. But we'll also switch over in a second to the last case study that I wanted to go over. Here we go. Mesh is coming in now. There we go. So you can see that those are meshed with shells. They don't appear to have a thickness on the mesh. It's applied as a kind of a property of the simulation, which is very handy for, again, reducing the element count that we need. And that's applicable for your constant wall thickness is kind of the assumption there. So the next customer inspired example here, this one I mocked up myself, was for like a gantry crane, or is actually an XY robot they were working on, I believe. But so basically looking at this, we also have beam elements we could normally use. So those big tubes there, big truss structures, we could represent with our beam simplification. But one of the important things with this setup, I'm going to have a mass hanging down off the trolley part of it. and fix these rails on the ends. One of the important things is the load transfer. So beams don't happen to allow no penetration contact, or that now what we just call contact. So I wanted to make sure that trolley sitting on top actually contacted the rails underneath it and wasn't just bonded to it, because that would add a lot of stiffness to the structure. And same thing with these wheels on the end. I wanted to actually have little wheels there that contact the rails that they act on. And that frees me up so I don't have to do a whole bunch of, kind of like statics calculations to figure out what the proper reaction forces and things would be at every location to simplify that stuff out. So that's always a decision you can make. Everything else in the study I'm going to bond, which would be kind of a crude approximation of welding it. And so these trusses aren't really acting as proper trusses. They're pretty much fused to the uh, rail here. So the breakdown of the different components, the truss wants to be made a shell almost entirely. I'm going to use shells instead of beams, even though they're constant wall thickness tubes. I could use beams, but I could also use shells if I want to. So that'll give it a little more detail and also allow me to do no penetration contact to them. And then the rails and everything on the side would be all solid mesh, and the trolley itself would be kind of a mixed. The thicker plates could be solid if they want to be, and the inner little reinforcements could be shells. This is just how I happen to approach it. So if you have a model that you know from the get-go, if I'm building this model just for analysis and I know I want it to be shells, then that's one of the kind of more rare situations where I might actually just model using surfaces. So instead of using a solid extrude or weldment, I'll just use the surface extrude command. And instead of mirroring and patterning features, I'll mirror and pattern bodies and then trim. And if you go this route, you'll get extreme performance inside the simulation compared to what's normally possible. So compared to trying to convert all these shells from a solid model, again, just to kind of show you the absolute basics of what I did here, I just have a sketch and I'm going to do an extruded surface instead of a extruded uh, boss or anything like that. And I'd set the distance I want that to go. And then when I want to mirror or pattern that, what would be like a structural member, whatever I'm going to be doing, like a circular pattern, I just make sure that I'm choosing, instead of features, that's actually a surface body there. So I'd be choosing bodies. And then that would allow me to select that and pattern the bodies around. So we end up having a whole bunch of separate bodies, and we'd start extruding or sweeping the cross members also in there to make up the truss. So I would eventually end up with something like this that you see. So this is the truss that I created, and it's 176 surface bodies, which sounds like a lot, and it is a lot, but the performance will actually be great because we don't need to convert these into shells. They're already trimmed nicely and everything. They're already basically we're ready to go as shells inside SOLIDWORKS Simulation. So the other component to this is I took advantage of a feature called import study features. So I actually defined on this part, I created a fake static study essentially, and I placed in all the shell definitions. So I actually edited all these to set their thickness and apply the material. And you could also apply mesh controls and things of that nature here on this static study on the child. And then that way, when I get to the top level, I can just run a command called import study features, and it'll basically pull up the definitions from the children studies into the top level, and it can also pattern it. So it would apply, those 176 shells twice to the two different members. So that's what I had done to set this up. I'll just quickly kind of pop open the results so you can see that the mesh that was generated. And so this whole thing meshes in a minute, believe it or not. It's again a crude first pass. We've got kind of bare minimum element sizes on things. But because we're using all those shells, we're able to do again, we did the local contact between the different faces here, face pair selection. And then the whole thing runs in actually just a couple of minutes. So if we go and look at the stresses or whatever plots we want to be seeing, very, very good performance for this size structure because I decided to go with that dedicated shell model. So even with the no penetration contact that we have going on, um, okay, I was cutting it, exaggerating a little. It's like a 4-minute solve time. And that's with no penetration contact between the rails here, the wheels and the rail, and then also with the trolley to the trusses. So I'm quite impressed by that level of performance that we can get. And this is the one where actually I'd be scared to mesh it live because meshing it with that new mesher was so multi-threaded that it locked my CPU at 100%, and it pretty much took all the power that my computer had during that period of time until it was done. So it's not something I'd want to be doing while I'm running the video feed here. Um, so I think combination, you can use the same approach, only really warranted if you're doing something really large scale and it happens to have a whole lot of these shell models then. Um, if you do decide to kind of build a dedicated model for simulation, again, doing all that work in SolidWorks outside of simulation ahead of time, you'll have a really easy time once you get in there. Um, so let me just show you, and maybe I can show it quickly, the import study features, and then I'll have to start wrapping up and just talk a little bit about some of the resources that you have. Again, if you're joining in late, make sure you scroll all the way up in the chat and get that resources PDF because they're all outlined there. But this is essentially a blank study I just created. So if I expand the truss, you'll see it all says thickness not defined for all the shells. And then if I were to run this import study features command, it lets you look at the components that have studies created on them and then turn on or off the features you want to import. So I'll just pull in just the material, the body type and material definition, and then say propagate to all instances. And this is going to run. And pretty much instantly, you can see there, all these shells now are defined because it reached into the child part study that was there and brought those up. And if I run the same command for the rails, um, import study features, it will bring over ahead contacts and things set up on those. So um, it can really save a lot. It's also very useful in certain circumstances where you reuse components across different assemblies and you want to perform analysis on them. It's kind of one of the ways we can pattern things around inside the assemblies. You see all these pin connectors came in with those rails, and the contacts came in with them because I had defined them on kind of a subassembly or subcomponent. Okay. Woo, got through everything here that I want to go through. The import study features command we just talked about. Also, last topic, I'm not really prepared to show anything, but the simulation API, you can use the macro recorder in SolidWorks and record your interactions with simulation. That was an enhancement a few years ago, and it'll help you generate a macro. So if you're comfortable with VBA or just writing basic macros, you can automate simulation that way. And the reason I mention this is there's some great examples in the PDF. Again, there's a resource. It actually gives you an Excel document like this. And if you just click those different buttons, the Excel document talks to SolidWorks, generates a simulation study, and then exports out the results back to Excel. So pretty cool. And all the sample code is in there. So encourage you to play with that if you want to. And to just keep learning, more you want to learn. There's tutorials built into SolidWorks for simulation. Not a lot of people might realize that, but with the add-in loaded, you can access those. A whole lot of different useful tutorials and validation examples. There's a great YouTube series from SolidWorks, SolidWorks corporate YouTube channel called Simulation Step Up Series that goes, like you'll see here, multiple 20-minute videos on specific topics like just bolt connectors and just contact, if you want to learn more about them. Several years old at this point, but still a useful resource. And then our YouTube channel, we're still uploading as many good simulation videos as we can. So check that out for additional resources. And then if you want kind of the next tier of options, those are all free resources. We have training courses, SolidWorks Simulation Training course we teach online. The core course to learn how to set up an assembly level simulation would be like 4 online sessions that are 4 hours long. So highly encourage you to take that if you're interested in learning more about SOLIDWORKS simulation. And we also offer services. So if you don't want to learn from the SOLIDWORKS textbook and instead you want kind of coaching one-on-one on your specific models, that's something Silvio and I both take part in, the mentoring and consulting. Um, so we can talk to us and we can always quote that out for you as a service. Uh, okay, and that is the end of my presentation. So I realized that was pretty quick there at the end, but I'll start going back through the questions with Silvio. Anything that you want to see again or hear more about?
Yeah, definitely let us know if you have any questions or comments there. You can put it in the Q&A, or if you just have any general comments, you can put it in the chat.
Yeah, and I just want to thank everyone again for attending too. It was a lot of fun getting the presentation together. And just don't forget to scroll all the way up and get those PDFs if you want them. We had the question on the weight of the surface bodies. That's a great point, and I didn't even mention, but I had turned on gravity. Anytime you're getting to like a larger structure analysis, you definitely want to consider the effects of gravity. So um, we have gravity turned on here in this particular study, and that's what's going to take into account the weight of the individual objects, the bodies and everything. So even something like I actually have a remote mass applied to represent the load. If I don't turn on gravity, then the mass isn't going to really do anything at all. So anything like that, you need to apply the gravity load to your study. It's really an acceleration due to gravity that's going in.
Hey, Ryan, you got a pretty good question out here about incompatible mesh.
Yeah, so we used to always advise avoiding incompatible mesh in general, and um, I think the verdict's still out on it a little bit, but in 2020 version of SOLIDWORKS drastically improved the incompatible mesh contact, the incompatible contact for bonding. And in 2021, they've taken that even further. So a lot of the hazards we saw of incompatible mesh bonding, which was things like weird stress concentrations that you'd get near those contacting faces, a lot of those are supposed to be resolved now in 2020 and more so in 2021. So in 2021, it'll actually be the default behavior. Even in 2020, they turned on incompatible mesh as the default behavior. It's essentially gotten a lot better. Um, so I would say if you're, it's difficult for us to weigh in because we're still testing it out too. But if you're really concerned about local stresses where parts are bonded, it's still probably a good idea to stick with compatible. But um, outside of that, the incompatible mesher now seems to be quite robust from all my testing. Basically, I think going forward, we'll see it become the default, and we won't be saying that you should avoid it anymore.
Yeah, ultimately the main thing to really be confident, which again, like Ryan mentioned, we are doing some testing, is really just doing some runs on your end to kind of see whether your results converge under those conditions and whether it behaves the way that you would expect. Like that's really going to be the final verdict of utilizing that approach.
Yeah, definitely. Yeah, it's always application specific in terms of making the final call. But I will say everything I showed you today was using the incompatible bonding. Anywhere I did have bonding, it was done with the default incompatible, and I didn't notice any strange behavior because of it. Um, so in maybe like back in 2016 or 2017 version, um, it used to be a very apparent thing. You could easily tell where the incompatible bonding was. Um, yeah, that's a great question, David, on where has this enhanced technology come from? Um, a lot of things were pulled down from Simulia, like I mentioned, the blended curvature based mesh algorithm. I don't know off the top of my head where the incompatible bonding improvements came from, but if you look at the 2020 SolidWorks What's New PDF, that's going to be the one that would go into detail there. And I believe it's even in this, to a lesser degree, this 2021 PDF also. I know it was definitely expanded on in here. So there's things like, there's all new in 2021, all new contact stabilization, what they call robust default interactions, improved bonded formulation. So there's even things like the feed is going to also cut off soon, but there's areas we used to have trouble, like Hertzian contact stress, that have been improved also. So I'm not sure how forthcoming SOLIDWORKS will be with where all the enhancements came from, but I expect that you'll see some pretty drastic improvement there in terms of the contact accuracy. So the 2021 What's New PDF, and then also the 2020 from the previous year is where you'd find that information. All right, and I think we'll have to shut the session down here, but again, thank you all for attending, and I'll try to reach back to you, David, I assume we have your email, so I'll try to reach back if I do find any more definite answer for that for you.